My name is Andrew Alexander, and I'm the project lead for Precision Hypersonics. So, as a team, our goal is to develop a custom control and data acquisition system for the Laser Spectroscopy and Chemical Propulsion Lab's upcoming high-enthalpy shock tube facility. A few semesters ago, Dr. P approached some of the members in his lab and asked if we could deliver a product which would enable him to make high-speed, precise thermodynamic measurements.
I'm Dr. Daniel Pineda. I am the principal investigator of the Laser Spectroscopy and Chemical Propulsion Laboratory here at UTSA. My research objectives include developing advanced diagnostics for extreme environments, which can include hypersonic flows such as planetary entry. These are situations in which the temperatures can get very high, like more than 5,000 Kelvin, and that's being able to develop diagnostics for those types of environments requires that we can recreate them in the laboratory. That's what the shock tube does. The shock tube is a device that can create high temperature, high pressure conditions, and it can help us understand the underlying spectroscopy of some of the diagnostic techniques, as well as help us test them in an environment where we precisely know what the temperature and the pressure is. To do this, I need something that's going to be able to determine when a shock wave arrives. And a shock wave is a very, very fast phenomenon. And so we need to make a measurement and make decisions based on that measurement on the order of a microsecond. And so that's what I need this device to be able to do. And that's why I need the shock tube control system.
So a high-enthalpy shock tube is a facility which enables researchers to examine scenarios that are similar to areas like hypersonic flight, chemical propulsion, and energy conversion systems. As I mentioned earlier, these kind of have some high-speed, high-temperature measurements. In order to make these measurements, our team developed the shock tube control system. So the shock tube control system is comprised of three parts: the data acquisition, which is the LabVIEW and software portion of the project, which actually measures and records data; the instrumentation, which is the physical implementation of sensors and transducers to measure time and pressure; as well as the controls, which is all of the electrical portions of our project, as well as all the mechanisms that will be implemented into the shock tube.
The instrumentation can be broken into a few different categories, first of which being the preparation for the shock. The instrument used for that is the capacitance manometer, and it'll give precise measurements of the absolute pressure of the gases going into the driver section of the shock tube. Second, it's important for Dr. Pineda to be able to identify the absolute pressure in both the driver and driven sections of the shock tube that cause the rupture of the diaphragm. To accomplish this, we are using static pressure transducers. Third, it's critical to measure the speed of the shockwave as it travels down the shock tube. In order to do that, we use 5 piezoelectric pins, which act as time of arrival sensors. These sensors also trigger the data acquisition system to start recording measurements from the dynamic pressure transducer, which measures the pressure of the reflected shock. As a whole, the instrumentation aids in not only the preparation for the shock, but also provides data to Dr. Pineda, which enables him to make calculations of both the velocity and pressure of the shock waves.
The goal of the data acquisition system was to collect data from the previously mentioned sensors and record it on a computer for post-processing. To do this, the National Instruments platform was used, including a hardware and a software side. For the hardware side, a BNC block, a chassis, as well as a PXIe card was utilized. For the software side, the LabVIEW program was used to develop a virtual instrument. This virtual instrument served as a user interface for a person running the shock tube to perform and record test data during a shock tube test. Due to the high wave velocities generated inside of a shock tube, a data acquisition system with an extremely high sample rate is required to collect adequately time-resolved data. For our system, this translates to a sample rate of 14 million samples per second per channel, which allows Dr. Pineda to perform the laser diagnostics that he specializes in. During testing on the detonation tube, our goal was to determine that the data acquisition system and instrumentation were properly working in tandem to detect and react to a shock wave traveling in the hypersonic Mach regime. Upon completion of the test, in comparison with high-speed, time-resolved video footage of the wave, it was determined that our system successfully detected a shockwave traveling at above Mach 7. Additionally, the uncertainty associated with this measurement was 7 orders of magnitude smaller than the measured value of the wave speed.
Earlier, we talked about the data acquisition as well as the instrumentation for the project. Here in the physical control structure, everything comes together into one central location. We have storage for the National Instruments hardware as well as other auxiliary equipment for the shock tube. And here on our control panel, we have readouts for all of the instruments so you can see the values that those are reading. We also have all of the physical controls for the shock tube by the form of these switches. These switches control these pneumatic valves, which will control what's coming in and out of the shock tube. This provides one central location where the user can see all of the readouts from the sensors, control all the valves, as well as see the LabVIEW virtual instrument on our monitors here. One of the major things that we focused on when designing this was the safety of the system itself. So we have this remote panel, which will be used in high pressure testing, which will be behind a blast shield far away from any sort of high pressure systems. We designed all of the lights and switches and the electronic system in such a way that it's always very clear to see if a valve is open or closed, if it's in the correct or incorrect position for various times within the test. All of the pressure systems that control our pneumatic valves also have backups in case the lab's power goes out or any other sort of emergency situations.
With the fall 2021 semester coming to an end, we are proud to announce the completion of our project. This project has been in the works for over a year, and we are very grateful for all the support and help we have received. I'd like to begin by thanking the Laser Spectroscopy and Chemical Propulsion Lab, most notably Dr. Daniel I. Pineda, as well as graduate researchers Joe McCloskey and Kyle Fetter. Furthermore, I'd also like to thank Dr. Christopher Combs and the UTSA Hypersonics Lab for enabling us to test our project. Thank you so much to Dean, who has enabled us by the construction of the detonation tube facility. Lastly, I'd like to thank a few members of the Mechanical Engineering Department, Professor James Johnson and Dr. Keith Axler, who taught Senior Design 1 and 2, as well as Dave Kunstler over in the machine shop for helping us fabricate our components.